different way of building I/O using lattice-based techniques.
So yeah, thank you for the introduction. Oh, okay, good, it's working. Okay, today I would like to tell you about our recent work on how to build lattice-based post-quantum I/O from a new assumption, a circular security with a random opening assumption. This is a joint work with Hsieh and Rachel. And non-negligible proportion of this talk, that some of the slides are stolen from Rachel's slides. So if you see something that is that seems familiar, you're correct. Okay, well, the first page is always the definition of I/O. It's probably the 5th time we see this in this workshop. So what is I/O? I/O takes in circuits and then obfuscates it into a functionally equivalent circuit, which hides the implementation properties inside the original circuit, in the sense that for any 2 circuits that are equivalent and they have the same size, the obfuscation outcome is indistinguishable. Okay? And we all know that I/O is super useful. Whenever we get a question in crypto, we don't know how to solve it, well, first try I/O. And also I/O itself is a very useful and primitive, if we are willing to believe in some reasonable but strong heuristic. When we want to use obfuscation to hide whatever natural property that we want to hide, well, I/O is a good candidate. Okay. So, good, we all want I/O. And we all now know that we can build I/O from some standard assumption, thanks to the work by JLS, from LPN, from local PRG, from pairing. And we also saw yesterday that we can replace some of the assumptions with other sparse LPN assumption. Okay, then the question is, what's next? What's the next thing we want to do? Well, actually, there's a lot of things we want to do. So first of all, we might want some I/O with better efficiency. We want, the current construction is fairly complicated, as you all saw yesterday. So we want something that's simpler. Particularly, it would be great if we can avoid non-black box use of crypto, like if we're stacking FE over FE or anything like this. On the other hand, we also want some, I call this improved security, or in some sense, we're trying to get things with better assumption. For instance, we are using 3 assumptions that are of very different type currently to achieve I/O. Can we get some less amount of the assumption? Can we get a different set of assumption? Can we avoid sub-exponential hardness? And in particularly for the main target of this goal, can we get post-quantum security? Well, in particular, we all know that any assumption over pairing, unfortunately, is now broken with once the scalable quantum computer is a thing. So this construction is provably broken under the existence of quantum computer. So we need some other approach to try to get post-quantum security. Okay, why do we care about post-quantum I/O? Well, we can look at this in 2 ways. So first of all, we don't yet have practical I/O. Sure, we don't have practical quantum computer yet, but we don't have neither. So on one day, it's hard to tell who comes first, right? So one day when we're trying to really use I/O, well, it might be the case that we really need post-quantum I/O to make sense. That's one thing. And another thing, on the more constructive side, I/O is also a very exciting primitive when we have actually quantum computer in use. Because with I/O, we can build a few very interesting quantum crypto objects, such as quantum money or copy protection type of stuff. So for these reasons, we want post-quantum I/O. Can we get it? Can we get it from LWE, which is probably the most powerful standard post-quantum assumption? Well, as we sort of saw from yesterday and today, this seems to be a fairly long shot. If we are our understanding of what we can do with LWE is down here, then I/O is sort of up in the sky. It seems very far away. And we don't even have a good hunch on whether or not it's even possible. Is it really it's buildable, or is it something inherent inside the LWE assumption that disables us from going to I/O? So therefore, we really need a space to play around these kind of goal. We need a space to make assumptions, and some of the assumptions in the heuristic might fail, but along the way, as long as we're not making the same mistake again and again, we're always progressing. We're knowing more and more what are the correct assumptions to make, what are the dangerous structure that we should not use, and hopefully this heuristic route will eventually get us to I/O from some assumption that either is a standard assumption or is a new assumption that after, I don't know, 10 years, then we become comfortable with. Okay, so this is to motivate our work. Now I start talking about how we will try to construct I/O from LWE or LWE-related primitive, or more generally, from lattice. Okay. We all know that LWE is super powerful on its homomorphism. So at least when I just started thinking about I/O from LWE, it seems surprising to me that we cannot do this from LWE, in the sense that we already know like any homomorphic, we know FHE from LWE, so we can homomorphically evaluate any function by just using standard FHE encryption. So, and we have many of them. So we can just encrypt the circuit. We can, we can homomorphically evaluate it. I can think of the circuit itself as a input, and then the actual input X I'm evaluating is the universal circuit that is encoding X. Then from every ciphertext of C, I can get to a ciphertext of C of X for every X very efficiently. We know how to do this from LWE. So what is the gap? The gap is that to achieve I/O, we need to get C of X in the clear. We want something that allows me to evaluate the circuit, not just evaluate the ciphertext of the circuit. So a ciphertext of the circuit is not enough. I really need some opening that allows me to get from a ciphertext of C of X to actual value of C of X. If we're doing this in an input by input manner, it is actually not that hard. If we think about it, it's sort of similar to what we know in like ABE type of stuff, or one key FE type of stuff. So basically, where's my, oh, good. So we know that, okay, assume that our ciphertext is some sort of additive ciphertext, then I can just give out the hint as the LWE path. If my ciphertext is padding my output circuit as this LWE path, then give out this LWE path, it's provably secure. This leaks nothing beyond the information of C of X, assuming the original encryption is secure. So what's the issue with this approach? Well, this approach is sort of useless in the sense that it is totally inefficient. If we try to reveal the ciphertext in an input by input fashion, then I can just as well give out the truth table, right? To achieve I/O, there's always one canonical way to get it, just by giving out the truth table itself as the obfuscation. So if we want an efficient obfuscation, then this approach doesn't work. I don't have the time to look at every of these ciphertexts. I also don't have the space to put in all of these individual hints for all the inputs. So the really core theme on constructing I/O from LWE is to achieve succinctness. I want a succinct opening that is much shorter than the whole truth table, but it's able to allow me to decrypt or decode whatever this operation is, every output bit of the circuit. And this is sort of the core hardness, I would say, to get I/O, and also we see these kind of difficulties in like different types of LWE-based construction. Oftentimes when we want strong succinctness, we found it difficult to get it from LWE. Okay, so let me zoom in a little bit about the succinctness. How succinct do we want our I/O to be? The standard definition of I/O, we want our size of our obfuscation to be polynomial in the description size of the circuit. Which means that it is sort of polylog in the size of the truth table. And also the time also needs to be efficient, so it's poly in the size of the circuit, it's polylog in the truth table size. Okay, this seems a very strong compression that is hard to achieve. Turns out, and one crucial challenge right here is that the obfuscation cannot even know the full truth table. It does not even have enough time to get every bit in the truth table to decide how you want to obfuscate things. So one great result that we know is that it's actually sufficient to look at this exponential efficient I/O. Okay, what does it require? It requires that okay. So for exponentially efficient I/O, we actually no longer have any restriction on the time of the obfuscation. I'm allowed to run my obfuscator is allowed to run polynomial in the truth table size. So the obfuscator has the power to read through all the truth table. All I want is a little bit of the size succinctness. I want the size to be slightly smaller, like polynomial, like a constant order smaller. Oops, that's not the right word. Yeah, it's like polynomial is smaller compared to the original truth table. And due to the work by LWE, we know that assuming exponential efficient I/O plus LWE, we know how to get compact FE, which in turn implies I/O. So this largely weakens the target that we want to, that we are going to do. We can focus on designing XIO, where our obfuscator can iterate through every input, and also and the goal is now just try to compress the obfuscation by a little bit. And finally, we also know that this transformation also works with XIO with preprocessing, which basically says that apart from this, you are also allowed to have a very, very long common reference tree. You can grow also polynomial in the truth table size. All it needs to do is that, all it needs to guarantee is that the CRS is independent of the circuit that you're obfuscating. Okay, so then back to our framework of trying to construct I/O from LWE homomorphism. Now, if we target only XIO, we have the time to compute all the ciphertext of every output bit. So in some sense, we can think about it as we have a ciphertext of C, and then using general homomorphic evaluation, we can get a ciphertext of the full truth table. And the remaining challenge is try to get something that allows me to succinctly decrypt this ciphertext, this output ciphertext. Okay? And this decryption, in some sense, because as an obfuscator, I know everything. As an obfuscator, I know all my encryption randomness, and all I want to do is to guarantee I give out something that is short and decrypts this ciphertext. Okay? So I can try to come up with a decryption hint that decrypts. That depends on all the secrets. Depends on the circuit, maybe on the secret of the encryption, and also on the encryption randomness. And also, we are allowed to have this CRS. And at the end of the day, what we want to guarantee is that this opening, which is very, very secret dependent, is something that only allows you to decrypt the truth table ciphertext and somehow keeps the original ciphertext, the ciphertext of C, untouched. That's the only way we can guarantee that the I/O security that for two circuits C0, C1 that are equivalent, the ciphertext is indistinguishable. Okay? So that's the sort of the only security goal here. We can it can be very leaky. It can have many lots of like bad information about the ciphertext. As long as the circuit is hidden, we're sort of good. Okay, and past work along this this paradigm, which can somehow be reduced to a easy to state assumption, usually would have an assumption that look like this. So it's a circular LWE with hint type of assumption. I will have some LWE, this is the familiar circular LWE samples that we all seen a lot. So I have public matrix, I have LWE samples, and then I circularly encode. I circularly encrypt some function of S with it. And this, oops, okay. And this circular LWE would sort of play the role of the encryption up here that we have. And this is something that we want to say that it hides a secret. It hides the message C right here. Okay? And also we would have, in the assumption, an extra hint or an extra leakage that can depend on all the secrets that we have in the LWE. And basically we want this hint to facilitate the opening process. So what are the hints that were useful in previous works? So there are actually a lot of them. In a very vague classification, we know some construction that use this link, that put some leakage of the secret, function of the secret as the leakage. And we also know some evasive LWE type assumption, which basically puts a matrix preimage, some short matrix T, such that B times T equals P as the leakage. This B would be sort of the public trapdoor, the public matrix. And also from GP21 and following works, there are also hints that are of the form opening R, which is essentially an encryption randomness of some ciphertext. So R is something such that when I plug in this encryption of 0, I get a known ciphertext. For some of these hints, when we're doing the decryption progress, when we are using the opening to get the final truth table, we also get some additional error leakage. We get some noise that is small due to some approximate decryption that happens a lot in LWE-based crypto. Okay, so although we have so many attempts along here, unfortunately, we often find the cryptanalysis attack against him. We know that oftentimes we got structural vulnerability just directly looking at this hint. And these, the feature of these attacks is that oftentimes they don't look at the samples along with the hint at full. Most of the attacks just look at the leakage itself. Either it's the hint that you directly give out, or the decryption error that sort of is leaked naturally when you do the truth table decryption. Okay, so unfortunately, prior to this work, there's no assumption that is unbroken, and we know that implies I/O. Okay, so for this work, we try to come up with an assumption that avoids these kind of structural vulnerabilities that we can that we identify to be problematic. Okay, so the way we do this was we present the new circular security with random opening assumption, where our leakage is again a decryption randomness of some 0 ciphertext. Okay, so what's different? First of all, in our leakage, in our CRO assumption, we strictly require that the ciphertext that we're opening is marginally random. What does this mean? This means that if the ciphertext is marginally random, then of course when I get a encryption randomness, it's marginally random. This means that if I just look at the randomness itself, it does not leak any information. Right? I can provably argue that any attack that only looks at the leakage itself doesn't work. So this differs from the previous work that has similar opening as their leakage. And also the second feature, which is sort of a natural feature that will come with these kind of opening type of leakage, is that there's no natural noise leakage. When I give out this randomness R, this randomness R emits this equation. This randomness R tells you that if you plug it in to the encryption algorithm with message 0, you get some ciphertext. So there's no natural leakage that will pop out from the decryption process. Okay, so our claim is that this gives a new cryptanalysis target in the sense that the LWE samples are circular LWE samples, which are more or less comfortable with. They are sound, assuming that we don't break circular LWE. The leakage R itself is also sound. If I only stare at the leakage, there's no structure that I can see from the leakage. It's statistically random. And finally, the naive combination between the leakage and the LWE samples. Basically, when I use the leakage actually in its like designed way with the original circular LWE samples, there's no error leakage that will come out. So this already avoids all the known attacks that we have for all the existing works. And therefore, we believe this is a well, we can see it in two ways. On one hand, this might be a more secure assumption compared to something that we might want to believe in. And also, on the other hand, this is a new cryptanalysis target. This is some new things that people haven't studied yet, and we want more cryptanalysis effort on it to understand whether or not there is some non-trivial way of attacking this assumption. And either way, this will give us new knowledge along the this kind of paradigm of using circular database sample with hints, and then hopefully it will progress our field toward a I/O construction that maybe will convince everyone. Okay, so now let me try to tell you how our CRO assumption look like. Okay, to describe our assumption, the first thing is to describe the leakage, which is a random opening. We said that it is a random opening for an encryption scheme. Which encryption scheme? It's the RegF encryption scheme. So the RegF encryption scheme, we have a public matrix B, which is essentially an LWE sample. We have encryption randomness, which is a low norm matrix R. And we can encrypt our message on the last row of the product. Okay? The resulting ciphertext would be something like this. The upper part is a new LWE public matrix, which is computed by B times R. And then the final line is a LWE sample padding the message X. Okay? We have linear decryption of it. It's not too relevant for us. The most important thing for us is what is an opening for this ciphertext. So the opening essentially is whatever encryption randomness that emits the encryption result. Okay? So an opening of the ciphertext with respect to this public key B bar is whatever R prime, that is small, and then B times R prime equals the ciphertext minus the message it encrypts. Okay? And then what's a random opening? A random opening is essentially an opening that is random conditioning on the decryption result. Okay? And by random here, because we want R to be low norm, by random here we always mean R is sampled from a IID Gaussian. Okay? And our hint is a random a random opening of a zero ciphertext. And zero ciphertext is just that there's no message encrypted. Okay? So why do we care about RegF encryption or the opening of RegF encryption? Well, there's a nice probability of equivocability for RegF encryption. Basically, we can think of this in this way. In the real world, my public matrix is an LWE sample. I can sample a Gaussian encryption randomness R and produce a encryption of 0. Okay? And statistically, it's always the same to say that, this is the same as I sample a random ciphertext of 0, and then I set my opening R to be random conditioning on the encryption output this ciphertext. These two distribution is the same. Okay? Now, the equivocability says that in the ideal world, when I try to switch my B bar into an unstructured matrix, I try to switch B bar into a random point matrix, then actually for whatever ciphertext I have, I can always explain it as an encryption of 0. Okay? This gives me a way to switch from the structured world where I'm working with a real public key and a real ciphertext of 0 into a random public key and whatever ciphertext. And also another good news is that this ideal world is actually efficiently realizable if I just sample B bar with trapdoor. Okay. Okay, so with this equivocability, we can already give an abstract view on what the circular random opening assumption is trying to do. So we'll have some RegF public key B bar, and then we will have some circular LWE sample. We want a special evaluation function f. Don't care about what this is for a moment. It's very special. We want it to produce a ciphertext, which is a RegF encryption of 0. Okay? And then the hint that we're going to give out along this assumption is a random opening of the ciphertext. Okay? So the adversarial view sees the regret public key, I see all the samples, and then I see the hint. I see R, which satisfies this equation, B bar R star equals ciphertext. Okay? All these things are well defined in the ideal world when I just switch my public key, B bar, and my all these database samples to random. Okay? When I have random samples, there is no more guarantee that whatever I compute should be some legit ciphertext of 0. But still, the sampling is still well-defined and valid. Okay, and finally, there's one thing that we require from CRO. We said that our circular random opening needs to open for a random ciphertext. So that's required here. So our CRO guarantees that the ciphertext is a random regret ciphertext of 0. And therefore, in the real world, I would have that the hint that I get is indeed marginally statistical random. Okay, that's the core property that we want. And also, this implies that in the ideal world, where I switch all the samples into random, the ciphertext that I derive from the spatial evaluation would be something that is pseudorandom. And therefore, the hint that I get would also be pseudorandom. Okay? And the CRO assumption states that for specific samples that we will specify later, and for the specific, and for a specific spatial evaluation function f deriving this hint, these two worlds are computationally indistinguishable. Okay. So looking at this, there will be two direct questions that one might think of. So first of all, what indeed is this spatial evaluation function f? Why would I have a evaluation function f that outputs a encryption of 0 naturally? And also, it's not just an encryption of 0, it's a random encryption of 0. Why would I have such a evaluation function f for some strange database samples? And also, is it useful for I/O? Like if we look at this, this looks nothing close to I/O, right? So let me answer these two questions one by one. First, let me try to persuade you that actually this sample and evaluation procedure is kind of natural. Okay. So the property that we're going to introduce now is the re-randomizability of regf encryption. And this is sort of the source where a random 0 ciphertext will pop up naturally. So this is the recall of what regf encryption looks like. And then we know that if I have a regf ciphertext for some arbitrary randomness, where the encryption randomness is short, if I add it with a fresh regf ciphertext, where the randomness has is Farmer-Gaussian with large enough norm, then the sum of them will look marginally statistically close to a fresh regf encryption ciphertext of X. Therefore, if I sort of have randomization inside my homomorphic evaluation, and the computation outcome is 0, then my output ciphertext will be a random, marginally random regf ciphertext. Okay, and this will be, okay, we also need to introduce the GSW homomorphic ciphertext. So this is probably the most well-known FHE ciphertext when we talk about these kind of fancy constructions. So it's the GSW FHE is actually very, very related to regf. Basically, the public key is also of this regf public key form. And then whenever we encrypt a message X, we encrypt it using a similar way. We have B bar times random R, just that we encode our message X by X tensor G. G is the gadget matrix. Okay? And we know that we can do whatever homomorphic evaluation we want. We can do addition, we can do multiplication, we can do unbounded if we additionally have the encryption of the secret key R. Okay? And one important feature that we will use is that it can actually allow homomorphic evaluation to real vector, like ZQ valued vectored function. Okay? So I can evaluate to not just bits, I can evaluate to some f of x which is inside ZQ, and I can actually just put it directly inside the last row of the encryption. Okay, so this tells me that for any function that takes in bits input and then maps to vector output, I can actually get out a regf ciphertext with some homomorphic randomness RF. Okay, and then this randomness after homomorphic evaluation is something that is efficiently computable, but depends on the original encrypted message X. So this is something that is not secure to reveal. And that's sort of why we need re-randomization. Okay. So now we can really display what our sample is here for our CRO assumption. So in our sample, we have a GSW ciphertext, which is circularly encrypting its own secret. Yep.
Maybe just a high-level question. So, like you have this general template, right?
Yeah.
And you set some properties of sampler that you want to satisfy. Are you making the strong assumption that that this template is generally secure, and then there's like a specific version you need to construct the IO, or?
So we only need a specific version of to construct IO. Right. So we only need a very specific version of sampler and a very specific version of this evaluation function for IO. Yes, I'm trying to show this specific version. For general version, we don't have an attack, but we also don't try to assume the fully strongest version, because oftentimes that's where the problems will come in. Right. Yeah. Oopsie. Yeah, any question? So yeah, so good. So thank you for the clarification. We're trying to display the explicit, so our CRO assumption uses very explicit sampler and very explicit function, and I'm trying to display what sample and what function we're trying to use. Okay, so the sample would contain a GSW ciphertext along with a fresh GSW ciphertext or regf ciphertext of 0 that is going to be used for re-randomization. Okay, and then we have some crazy stuff, which we can just vaguely view as some two circular LWE encryption. So it's just some LWE encryption, encrypting some circular message, some LWE encryption, encrypting some circular messages. Okay, and now what's the evaluation function? The evaluation function is very natural. I'm just evaluating some function f, which don't specify just yet. I'm evaluating some function f, and I get some GSW or regf encryption of with some dangerous encryption randomness RF. I randomize it by adding it with the fresh HT0 to get marginally fresh encryption of FFR. Finally, I subtract FFR by explicitly requiring that, okay, I'm only working with this type of functions of R such that it can be simulated using the samples that I have up here. So I'm not working for any function f. I'm working for some function f where the f of r is some evaluation outcome of these samples. Okay? So at the end of the day, the ciphertext that I get is indeed a marginally fresh regf ciphertext. And then the hint that I'm going to give out for the assumption is the opening for this ciphertext. Okay? It's re-randomized, so it's marginally random. Okay? And what happened in the ideal world? In the ideal world, there's no structure up here. Everything is random. The HEVAL procedure is well defined, but whatever it computes, it's something arbitrary. Randomization gives something arbitrary, and then finally, whatever I compute in this f tilde of sample, when I'm working with random inputs, there's no guarantees on it, but I can still give out a hint such that it has satisfied that the ciphertext looks like a 0 encryption with respect to this random public key bar, and we claim that, and we know that assuming circular security, the marginal distribution of this R star is computationally close to random, and we want to claim that, well, along with all these samples, these two worlds are indistinguishable. Yeah.
Even in the ideal distribution, you're expecting the matrix will have a trapdoor?
So in order to argue, okay, in order to argue the computational distribution is indistinguishable to random, we will need to like switch to a world where the public matrix B bar has trapdoor. But we know that these two worlds are close, right? These two worlds are statistically close.
At some point, you'd be using LWE with respect to that matrix as well?
At some point, I'm using LWE. No, in the ideal world, there's no LWE, right?
With respect to the matrix B for which you're assuming the trapdoor.
With respect to B, no. There's no LWE there.
Isn't HCT 0 with respect to B?
Are you talking about the real world or the ideal world?
Just, yeah, in the real world, then it's...
In the real world, these public matrix B bar or public key B bar are of the form LWE samples, right? These B bars are, I should have put it somewhere here, but yeah, it is B on the top and then an LWE sample RB plus E at the bottom.
Is the hint computed here?
The hint, okay, good. Okay, that's the, so we can view it in two ways. So first of all, from the CRO definition itself, it seems that R star is something that is inefficient. It's not something we can efficiently compute, right? But just like when we talk about, oops, it's a little bit far away. Just like when we see here, we can compute this world where we have a public matrix B and then a ciphertext. I can do two things equivalently. I can first have my ciphertext sample, and then I inverse sample R star. Inverse sample this R, which is something that is inefficient. Or statistically, it is the same. I can first sample R, and then I have my ciphertext. Okay, so that's the same thing that will also happen in the our CRO. So in this real world, actually the distribution of R prime is as good as a resampled R prime. Right? This R prime is marginally random. Okay? So
Changes, right? It's like the events are in different, I mean, when you define the event, that the event is just, okay, you're specifying a condition, that this is the condition. Condition is that BR star is equal to CT.
yes.
Yeah, in this real world, everything is structured. So this version is corresponding to I sample the random ciphertext first, and then I reverse sample the randomness.
Yeah.
But in this real world, you can also sample it forward, which you sample R star first, and then you reprogram. In some sense, you recompute B bar R prime. But this two ways of sampling doesn't exist in the ideal world. In the ideal world, there's only one way of sampling, which is if you know B bar is having a trapdoor. But if you only care about the falsifiability of this assumption, the challenger will always have an efficient way of generating either the real distribution or the ideal distribution.
My concern is only in this one in the real world, if the challenger has a way, or the reduction algorithm has a way of sampling two different R's, such that they sample to the same CT, then there might be a way to compute the trapdoor itself in the real world. I'm not too sure, that's what I'm trying to get at. Maybe there's no
But
way.
in this world, that like whatever that the sampler samples, R prime, like R star has a distribution, so it just samples something and gives to the attacker.
Okay.
Right? Attacker doesn't have a way to sample a different R star.
Not the attacker, the reduction algorithm. When I'm thinking of a proof in a sense, in that particular.
The reduction algorithm also just get the R star directly from the challenger, right?
I see. Okay.
Yeah. Okay. Yep. So this is the very, very specific version of our CRO where F and F delta and all the circular samples are fully specified, just to demonstrate that we only need one version of the CRO assumption. Okay, but I'm not going to explain this, and we don't need this at all. Okay, so now let me, oops, I have 15 minutes left. Let me switch to how we build XIO from CRO. Okay, so recall that in order to build XIO, we want some succinct opening for this ciphertext, and I want to hide my circuit C. Okay, and the tool that we're going to use is the dual GSW encryption, which can sort of also be viewed as the dual regf encryption with some specific input encoding. Okay, I would have some public matrix that is very wide. This is important for my compression. And public message is very, very wide. And then I will encrypt my message in the X tensor G transpose. Okay, so what matters the most here is that I can do homomorphic evaluation and obtain a ciphertext of some vector valued function g of x, such that this secret is much shorter than the size of the g of x. Okay? And again, this W and E are something that is very input correlated. Okay? And it's okay, good. Okay, so the nice thing about dual GSW encryption is that we will have a very short opening. So that if I'm willing to reveal WG, which is, of course, insecure to reveal, but put it aside for now, if I reveal WG and can directly get the long G of X, and then this allows me to, okay, good. This allows me to do succinctness that was required by exponentially efficient I/O. So essentially, I just think of this function that I'm the X that I'm encrypting is the circuit the circuit that I try to obfuscate, and the function that I'm computing is a chunk of the truth table of the circuit. Okay, and then I would have many chunks. I would use like a square root of the truth table size many of chunk, and then every chunk is the size of the square root of the truth table. Then I would have square root many truth opening. Each of them are short. The full overall size is square root. And also I would have my initial ciphertext, which has square root of truth table size, and it's also much smaller than the truth table. Okay, so this dual GSW encryption is very has a high compatibility with what we want on the XIO succinctness. The only issue here is that this WG, as we said, this is something that depends on the initial encryption. Right? This is something that when we're doing I/O, this is something that depends on the circuit. So we cannot just reveal it. And also, if we revealed it, it will also reveal the dangerous noise leakage E. Okay. So the trick here, if we use the same terminology that Nico used, we are trying to add a wait, what's this? Special encryption or magic encryption? Yep, thank you. Magic encryption. We want to add a fresh SA plus E to pad this, and then if it's fresh and when I open SI plus WG, we're good because it's fresh. So the opening is random, and the leakage, if we use a EI that is much larger than the scale of EG, it floods the dangerous error. The thing is, how does this come from? We want to add this to our final ciphertext, but this cannot come for free. It has size as large as the truth table, so if we just give it out, it's doomed. So we will think whether or not we can use some homomorphic evaluation to help facilitate this. So we can imagine, okay, we want some succinct representation for this magic encryption. So you can imagine that I have an encoding that sort of encrypts S and E. And then I want some homomorphic evaluation that computes SA plus E. Okay? Of course, we all know that's a homomorphic encryption. Therefore, whenever I compute SA plus E, it will come with some pad that I will need to open. Okay? But I don't want to open it again. If I try to open it, then we're back to the same regime. Now, the whole reason that we try to get this fresh magic encryption is to try to refresh the opening. And if we want to reopen this encryption, then we're going nowhere. Okay? So, and also there's another challenge for this framework is, wait, it's not working, okay. So there are two challenges, basically. The first challenge is that I need to somehow make sure the ciphertext encryption is much smaller than the final pad that I'm giving out. Finally, I'm giving out SIA plus EI. I want to make sure this encryption or encoding is shorter. And this already seems kind of challenging in the sense that if I'm encrypting the error EI, the dimension is as large as the truth table. Okay? And secondly, I want to avoid the need to open this output ciphertext. Okay? So how do I do that? Well, there's one hope. Can we think of this ciphertext? If we look at this, this is sort of a LWE sample with error with secret being this evaluation UI plus SI we want, and the error being this evaluation error plus this EI we want. Can we view this ciphertext as a good path? Well, not yet, because we know a homomorphic evaluation would have these paths dependent on the message we encrypt. Therefore, this marginal distribution of UI plus SI can be very bad because UI might depend on SI, samely on the error. Okay? But we can imagine if we have some very special encoding to start with, and we have some special evaluation procedure, can we hope to make these independent? If we manage to get these independent, then the output ciphertext is directly a good path that we can use for as our magic encryption. And that's the goal of the thing that I'm going to do. I have 10 minutes left, oopsie. Okay, so let's try to break down and see how I can achieve this ciphertext with like independent evaluation path. Okay, so first of all, let's stare at this LWE sample, SA plus E. We know that we want to reveal it, but the thing is, EI is, the dimension of EI is as large as this sample. So how do I succinctly reveal it? Well, one way to look at this is that I can always find some delta that divides my modulus Q, and then I can separate my LWE samples into the higher order bits and the lower order bits. And the thing is, okay, so first of all, if I choose my delta large enough, the higher order bits is actually independent of my error. Now, if I set my modulus to be much larger than this delta, then the size of this lower order bits is just the dimension times the bit length of delta, which is much shorter compared to the final path that we try to reveal. Therefore, if we just publish it, we still get succinctness as long as we choose our modulus Q to be large enough. Okay? So this is the trick. Now we encrypt this EI using this lower order bits, and then we simply publish it. Now our target is to get this S tilde A plus E tilde, and with this lower order bits, the things we left with is trying to get a homomorphic evaluation of just the higher order bit. And then if I have this evaluation of the higher order bits, adding it up with the lower order bits, I get the LWE sample where this EI is totally independent with the evaluation error that I will get in this homomorphic evaluation. Okay? Therefore, if I evaluate my path this way, I make sure that the final EI tilde I get is actually something that's fresh as long as EI is large enough. Okay? And how do I get this homomorphic evaluation of the higher order bits? Well, I can try to homomorphic evaluate a encryption of SI. Because SI is succinct, this encryption can be short. Okay? So this is something that I can afford to publish. Now, the issue is that, again, if I'm homomorphic evaluating a function over S, this U evaluation path would be correlated with this S that I'm encrypted right here. Therefore, the distribution of this S tilde is still bad. Okay? Now we try to break the dependency between S and U. And the way that I do this is to rely on some linear, rounded linear decryption, such that I get the higher order bit of SI without doing complex homomorphic evaluation. And the way I do this is I start from, again, a succinct encryption of SI, such that it allows linear evaluation. So I encrypt SIG with some LWE samples. And we can see that to get SIA, I just multiply G inverse of A to this LWE samples. And then to get the rounded version, all I need is to round. Okay? I lied a little bit here because this equation is not always hold. It will have a rounding error, but that's fixable. I will fix it later. Okay, so if I believe in this equation for now, then using just linear plus rounding operation, I get the higher order bits, which I want, padded with some complex pad function of R. Importantly, it's only a function of R. It's completely independent of the secret S that we try to use. Okay, as I claim, it's fixable. I won't go through the algebra, but this works. Okay, now all I need to do is to remove this pad of R and make it back to the homomorphic evaluation. Well, and then I just stuck in whatever homomorphic evaluation I have, and then I would have my ciphertext being the homomorphic evaluation binding terms minus the pad that we want to remove. And this evaluation UI would be correlated to the secret that is encrypting, but that's fine because it is, in any case, independent with SI. Therefore, if I compute my magic encryption in this form, then I would have SI tilde, which is SI plus UI, where these two things are independent. And also this EI tilde, we also said that EI and the evaluation error is independent. Therefore, I get a fresh LWE sample, at least marginally. Okay. So far so good. It looks like I get a special homomorphic evaluation that allows me to get a pad that I'm going to use to pad my dual GSW encryption that's encrypting the function value. So what's the issue here? The issue here is that I know that SI tilde A plus E tilde is a random LWE sample, but it's random only marginally. What does it mean? In the actual I/O scheme, I will give out not just the opening that we use SI to pad. I also need to give out all these initial encodings in order to facilitate this evaluation. Therefore, if this SI tilde is not random given all these samples, I cannot really say that this SI can pad the dangerous opening that I'm trying to give. Right? I want SI to pad some secret WGI, but these are all in my view. So the question is, can I get SI tilde that is random given all these ciphertexts? Okay? And I want to argue that this is sort of something that we cannot hope for if we don't change our construction by some crucial way. Okay? Why is it the case? If we look at all these samples that we care about, so we are giving out these LWE samples, we can give out the lower order bits, and then we are trying to use SI tilde to pad something. And these things eventually needs to satisfy equation that after these, whatever complex evaluation they have, we're resulting in something small. So these LWE samples emits a correctness equation that means that when I'm plugging pseudo-random things inside these terms, it's unlikely that the outcome is small. So I cannot really switch these samples into random samples. I cannot say that they are random. Therefore, the best I can hope for is some sort of indistinguishability-based assumption. Okay, this is still legit. I can maybe hope that, okay, I give you these samples, I give you this S tilde padding some WF, and then I give another one padding WG. Given that the two functions are computing the same function, maybe they are computing the same functionality, maybe you can have some indistinguishability-based assumption. And indeed, that's, in hindsight, sort of what happens in a lot of previous constructions. And we want to challenge this in the sense that we want to argue that this is sort of problematic. What does it mean? Usually when we come up with an assumption, we say that, there's pseudo-random assumption and then indistinguishability-based assumption. But oftentimes, it's the case that we identify some hard structure through cryptanalysis that we really don't identify, there are structures that we really cannot find any useful structure inside. Then, so essentially there are structures that for cryptanalysis, it just looks like random. It gives me a sample, it just looks like random. And this is true for many of these assumptions, like LWE. We have a sample, we don't have any structure on it. We feel that it's random. DDH, we get a group element. It looks like a random element. And in that case, yeah, we can say that, okay, I want a weaker version of the assumption. I put an int-based assumption. In that case, oftentimes it's well justified. But this is not the case right here. Right here, we are actually facing a case where there's easy to identify structure inside my samples. In my samples, I already know my samples satisfy some relation. I know my samples have some specific structure that I can see. And then I want to fuzzily say that, okay, sure, there are some structures that I can see, but let's assume that I can still hide something. And of course, it's not true that this is generally impossible, but it's dangerous, because if we look at some of the attacks that we have, it's oftentimes that we are indeed using the structure that we see, and then we use it in a smarter way, and then we turn out we can break the indistinguishability-based assumption. So if we want an assumption that we have higher faith on, it's safer to think about assumptions that actually I can argue about pseudorandomness. Okay. Yeah, so I want pseudorandom version. There's one power that I have not used. That is, I can use the CRS. So finally, sorry, I'm running out of time. I'm going to give you a quick glimpse on how we're going to use the common reference string to recover the pseudorandomness. So the way we do this is some sort of CRS programming. So let's assume that for some strange reason, in my evaluation encryption, I actually include a regf randomization term. Okay, that is not super non-natural. If I have in my homomorphic ciphertext I have a GSW evaluation, I can always add in a GSW randomizing term. And this randomizing term is large, so I need to put R star in a CRS. Okay? If this is my correctness equation that I need to satisfy, then I can always do the same like inverse trick, right? This is the same distribution. Sampling in either way will give me a completely same distribution. But I can sort of think about I first sample the randomization term randomly, and then I sample my R star to satisfy this whatever equation it needs to satisfy. Okay? So why am I going through all these? The thing is, if we're doing things in this way, if we have this randomizing term in my CRS, I can actually switch everything to random while keeping everything well-defined. Right? And I can think of an ideal world version where I switch my public key regex public key to random. I can switch all my samples to random. And usually, it's not hopeful to say that when I switch these samples to random, it satisfies some equation that is of a specific structure. But once I add a randomizing term, I can program everything into my CRS. Okay, and that's essentially what we're doing in the in our CRO assumption. So I don't have enough time to go through a final CRO assumption, but at the end of the day, we'll see that these equations, when I expand everything, it is a regf ciphertext of 0. And we just program whatever correctness it needs to satisfy in the ideal world back into the CRS. Okay? And this gives us a hope to argue pseudorandom assumption, and that's exactly how CRO is formulated. Okay, so let me skip this part. This is just manually putting in the randomization of GSW inside our construction. And to be very specific, this is how it looks like. And yeah, so in some sense, this shows us how CRO should look like. I just put in all the samples that I have in the correctness equation. I know that in the honest world, whatever my evaluation outcome would be the randomizing term of CT. And in the ideal world, these samples will compute for some nonsense, but in either world, the hint is well-defined. And as long as I know that in the real world, this hint is a random regf cipher. Sorry, the CT is a random regf ciphertext. I know that even in the ideal world, when I stare at this hint alone, it does not leak anything. Okay. So yeah, sorry for the skip on the final few slides. And as a conclusion, I want to give a final view on our new assumption and new targets. We have a pseudo-random assumption for LWE samples, along with some marginally random hint. And with this assumption, we know that, at least if we are confident in circular security, we know that if I look at these LWE samples alone, there's no attack. I know that if I look at this hint alone, as we just say, it's random, so there's definitely no attack, provably. And finally, when I use this R directly, the only way that I can naturally use it is to compute the ciphertext back. But it's useless computing the ciphertext back because whatever the ciphertext is just something that is computable from the sample. Okay? So the new target is whether or not we can have some non-trivial ways of combining LWE samples or circular LWE samples, making things easier with this kind of opening. Does it give any new attack, or is this actually some good hint that we can give out? Yeah, and that's all. Thank you. Yeah, any questions? Yeah.
Thanks for the talk. If someone wanted to try and cryptanalyze this, do you think there's like some simple to state distilled version of your assumption that they should be trying to attack, or do you think it's really important to look at specific evaluation?
So depends on what, like how simple to state you want. There's always this version, right? We have everything specified. Wait, where is it? It should be somewhere around here. There's always the version that we have all the samples specified, right? We have, we actually can also specify the dimension. And we have all the circular functions satisfied, and then we have our hints specified. So yeah, you can look at this and attack it. And is there any easier version? That I don't know. Because sort of the justification of the security of the hint is actually that it is marginally random. And it's not that I can come up with marginally random hints that are interesting, right? So yeah. Any other questions? Yeah.
Just high level, kind of following up with this question. So my understanding is you have like a family of assumptions, you only need one.
Yeah.
But this one is arguably, it's amazing that you can get it, but it's not the most elegant to look at.
Mm-hmm.
While the general one, you conjecture is insecure for like similar reasons, right?
Sure, yes,
Something
indeed.
general. So in what way is it, it seems better, but in what way is it better than previous work where they try to, it seems like previous work has the same thing. It's like they stated the general assumptions, the assumption was insecure, but the specific version was also not broken, the ones that they need. I'm trying to see in what way is it still better.
Okay.
It looks like very similar as that.
So first of all, the general version of our assumption is also not broken. No, we don't have to be honest, I don't even have another version of this, these F and F tail that satisfy the precondition, but yeah, the general version is not broken. And also, I think the one principle that I think our assumption differs from the known assumption is that we identify some attack strategies. And then these attack strategies attack the existing assumptions. Sure, the construction is not broken, but there are some attack strategies against those assumptions. And our assumption is provably secure against these strategies. Yeah. If we provably say that the hint itself is not leaking anything, we provably say that the error leakage is gone. Right, so yeah, it's of course it's definitely not the end goal, but I think it's one step forward. Yeah.
So in the interest of time, we should probably take other questions offline.
Yeah.